The broadcast is now starting. All attendees are in listen-only mode.
Good morning. Welcome to the Copper and Brass Service Center Association's webinar. Today we are proud to have with us Tom Christie and Larry Muller from Chase Brass and Copper Company. Tom is the National Sales Manager and Larry is the Manager of Metallurgy and Technical Services. My name is Cindy Launchbaugh and I am the Director of Marketing for CABSA and your host today. Tom and Larry will take a look at the new legislation that will have a significant effect on the brass rod industry in the near future. They will be addressing each piece of legislation. They'll provide a timeline for when that legislation will take effect and how it will impact material choices. You will also learn about certification required and the alloys now being provided by the industry. During the presentation, everyone is encouraged to send questions to our presenters by using the Questions tab on your webinar toolbar. I will collect the questions and then read them for our presenters at the end of the presentation. If you are interested in additional materials following the presentation, please send an email to Tom Christie at tchristie@chasebrass.com. Now, without further ado, I would like to turn the presentation over to Tom Christie and Larry Muller. Go ahead.
Good morning, everyone. We really appreciate the opportunity to talk about the dynamics affecting the brass rod industry and what we're doing to address those changes. My name is Tom Christie. I'm the National Sales Manager. And just to start out here, some of you may or may not be familiar with Chase already, so we'll just do a brief introduction of the company so you have a feel for where we're coming from. So the company actually traces its roots back to 1837. We started up in the Waterbury, Connecticut area. We've gone through a series of ownership changes. Most recent in 2007, we were actually acquired by KPS Capital Partners. They formed a company called Global Brass and Copper, of which we're one of three divisions, along with Olin Brass and A.J. Oster. We're centrally located in Montpelier, Ohio. In 1965, this facility was constructed, and Montpelier was selected because it was really the geographic center of brass rod demand at the time. And we did a study here about 15 years ago and found that that center of demand had only moved about 20 miles to the west. So as far as geographic location to support current demand, we're still pretty well situated. We do employ approximately 300 people. That's a combination of both hourly and salary employees. And we're currently producing leaded, low lead, and lead-free alloys. And again, the leaded and low lead and lead-free will be the focus of the presentation today and what's really driving that diversity of product. Our product is produced as rounds, hexes, squares, and special industrial shapes. And we only produce solid brass bar stock here at Chase. Our size range is 1/4 inch up to 4.5 on standard extruded product. And then we also have a cast and turn product that ranges from 5 to 9.5 inches. This facility originally, when it's constructed and along with all the advancements and automation added, initially the focus was to really make one product, Alloy 360, and make it in large volume and very efficiently. As the industry has evolved over the last 40+ years, the dynamics affecting that need for product and the legislation impacting our industry has been substantial. And so what I'll do now is turn it over to Larry Muller and let him really focus on those legislative issues that are affecting our world and ultimately your customers' worlds, and what we're doing to help provide solutions to meet those challenges.
Well, thanks, Tom, and thanks to all of you out there that chose to spend your time with this webinar this morning. The drivers of change is getting to be kind of a long and complicated list on a timeline here. The best way that we could figure to present this busy subject matter of all the activity that's occurred over the last 5 years was to get you to just focus on the different areas where change has occurred. Federal legislation, which I hope is self-explanatory about affecting every product that's made in the U.S. Then there's the legislation enacted by the states to control the product that is supplied to commerce in their state. And then there's voluntary standards, which are the requirements created by industry groups that are comprised of a balanced level of users and producers, and either make or change standards in reaction to federal and state legislation, or to meet a need that they don't believe will be covered by states or nationally, but still needs to be incorporated in products that are sold to consumers. The other way that we're trying to make this a little bit simpler to understand is to forget a lot of the interstitial material and just have you focus on the red items, which represent the culmination of the changes that have occurred in the past. So let's start at the bottom of the table, and we'll go through the highlight items first, and then we'll talk about them in a little more detail in the following slides. If you look at the bottom in the row marked earlier, it all really began with the Safe Drinking Water Act. And since I can't see your faces out there, I don't know if this would be considered ancient history, but in 1974, the government approved this act in order to protect all sources of drinking water, except for, I think it said, private wells that serve less than 25 people. The Safe Drinking Water Act was modified a number of times over the years. In 1986, the act was changed to ban soldering materials that contained more than 0.2% lead, and then any drinking water components that contained more than 8% lead. Along the way, in 1991, the lead and copper rule was introduced and approved, and what this did was set the amount of lead that could leach into drinking water in a standardized laboratory test to a maximum of 15 parts per billion. That's with a B, billion. In 2003, there was an event, which I guess is the most politically correct way to phrase it. There was an event in Washington, D.C. where they changed how they disinfected the water, and it resulted in a large release of lead leaching into drinking water. Well, things didn't happen that should have, and things happened that shouldn't have, and it began a number of efforts to enact legislation to restrict the amount of lead in drinking water components. And they culminated in 2011 in the signing of Senate Bill 3874 by President Obama, which restricted the amount of lead to 0.25% on a weighted average basis in anything that touched drinking water. At the same time, the Consumer Product Safety Improvement Act, which was first approved in 2008 and affects products that are used by children aged 12 and under, put into effect a requirement that if it's considered to be technologically feasible, that those children's items will contain no more than 0.01% lead. So quite a change from 1974, where, as far as lead was concerned, almost the sky was the limit, down to a 0.25% weighted average lead, and we'll talk about what that means in a minute, and then 0.01% lead, which is 100 parts per million for children's products. Looking in the state legislation column, one of the momentous defining acts occurred as early as 1986, and that was California's Proposition 65. And that sufficed for California until 2006, when their state legislature passed AB 1953, which is the model for the federal legislation that was passed in 2011 of this year, and set the 0.25% maximum weighted average of lead in drinking water components. A couple of years later, Vermont passed the same law under their own designation, and then other states were considering it along the way, but aren't really necessary anymore now that the federal legislation, 3874, has been signed and approved. In the voluntary standards column, there are three major items to really consider. NSF 61, and NSF 61 is the Drinking Water System Components Health Effects Standard, set a maximum lead leachate to 5 parts per billion, so significantly tighter because it's not a linear change from 15 parts per billion to 5 parts per billion, but a significantly tighter requirement for lead leachate. The International Code Council passed a fire suppression standard, which says that all new 1- and 2-family homes beginning in 2011, where this has been introduced into the municipal codes, has to have a fire suppression system, in other words, sprinklers in every room. And those are tied into your drinking water systems in the home and are designed to ensure that the materials that are used work as required by incorporating NSF 14, which is for PEX standards. And PEX standards are the plastic tubing that now are used in many homes to convey water around as opposed to soldered copper tubing. And NSF 14 has some corrosion requirements that had not been seen before, but were a reaction to some corrosion failures in Nevada and Minnesota earlier in the decade. Over the course of time, beginning with the Safe Drinking Water Act in 1986, a lot of companies stopped using high lead alloy castings or high lead content brass alloy castings and shifted to brass rod with a lower lead content. In addition, in order to meet the 15 parts per billion of the lead and copper rule, they started to use surface treatments to remove surface lead, so that in that standard laboratory test that's conducted by a number of certification agencies, they would be able to pass the 15 parts per billion and hopefully prepare them for the 5 parts per billion lead leachate that's required in NSF 61. Regardless of what material they choose, ultimately these companies which make faucets, valves, and fittings have to comply with federal, state, and voluntary standard requirements, which tell them what to use and how to use them in the grand scale of things. If there's one piece of good news for manufacturers from all of this, at least now with the national legislation passed, that's 3874, they're dealing with a national standard and instead of facing a jumble of individual state standards. Although there's still a possibility that if states want to go to tighter standards, they can do so. Okay. Whoops. To look at a little more detail on some of these various pieces of legislation or standards, we don't really know what people or customers will end up calling the national law. It could be S3874. It could be the Safe Drinking Water Act. It could be law number 111-380. Regardless, the important thing to know is that it was signed on January 4th of 2011. It restricts the amount of lead, as we mentioned, to 0.25% weighted average maximum, and it goes into effect 3 years after the date of signing. So January 4th of 2014 will be the effective date for the national legislation, and that delay was requested in order to give companies time to transition all of the product that they were making for states besides California and Vermont to meet the requirements across all 50 states. The important part of the legislation that affects the products that we're talking about today is shown in the oval here. That the term lead-free means that there's no more than a weighted average of 0.25% lead when used with respect to the wetted surfaces of pipes, pipe fittings, plumbing fittings, and fixtures. And what that means is shown in the NSF 372. that was developed in order to help explain first the California requirement for a quarter weight or quarter percent weighted average maximum, and now the national legislation. The requirement is that you look at every component that touches the water and the maximum amount of lead that that material can contain. It doesn't matter what that actual sample might contain, but if it's alloy 360 and it has 2.7% lead in the sample that they receive, they look at the ASTM standard for alloy 360 and say, potentially this could contain up to 3.7% lead, and so we're going to use that value. Then they look at the wetted surface area of that component. They total up if there's more than one component, all of those different things, and divide it by the number of components, and they come up with a value which, if it's above 0.25% weighted average, means that it fails. The particular requirement of this standard, though, also indicates that no matter what you do to the surface to reduce the amount of lead that's in touch with the water, or if you put a coating on there, that's disqualified from the calculation. They use the bulk materials lead content for the calculation, and these other types of treatments are not considered part of what has to be done.
And Larry, I think that's an important comment to make a distinction of. Previous to the California and Vermont legislation, which ultimately drove this national legislation, most of the requirements related to our customers' products were leachate and therefore performance-driven. So they could get away with coatings or washes typically to still be compliant. This evolution of this legislation really is saying they are very focused on the content of the metal, more a prescriptive-based legislation as opposed to a performance-based legislation. So this has been a substantial impact and deviation from what our customers have previously had to deal with compared to today.
Thanks, Tom. And what continues, though, from what they've had to deal with to the new legislation is that they have had to have their products certified by a third party, and that continues. It's not inexpensive to comply and to get certifications made, and that will continue. It's also much more expensive, though, not to comply. So the paperwork requirements continue for everyone who's been supplying water components up till now. NSF 61, we talked about. NSF used to stand for the National Sanitation Foundation. They're involved in the certification of lots of different things. If you look on food processing equipment, for example, much less these individual water components, you'll see the NSF stamp on them. And this requirement to drop, as it shows in the oval at the bottom, the amount of lead that can leach into drinking water in their standard laboratory test from 15 parts per billion to 5 parts per billion was first voted in 2007, but producers were given 5 years to comply. And the hope here was that by having a tighter lead leachate requirement, that would supersede any form of additional state or federal requirements. But as you can see now, there's the double impact of 5 parts per billion and that weighted average lead maximum of 0.25%. The types of materials that are used for PEX fittings. As a result of some significant field failures over the last few years, now incorporates a dezincification resistance requirement as shown in the upper oval here. And that means that in a standardized international type test, parts cannot exceed 200 microns in depth, and that's 0.008 inches, 0.008 of an inch in that standardized test. If it does so, then it fails. That same material cannot show any proclivity towards stress corrosion cracking in a standardized stress corrosion cracking test. We'll talk about that a little bit more. But what that means is that in stress corrosion cracking, when you have a combination of stress, high levels of stress, and then an environment that attacks the grain boundaries of the material, and in this case, when we're talking about copper alloys, that's ammonia or amines, think Windex, it will cause the part to crack in a very short period of time, whereas in the absence of either one of those two factors, it won't crack. And the things that affect the amount of stress that a part's under is how the material is produced, how the parts are produced from that material, and then the installation of those parts. Dezincification resistance is a little bit easier to show. And when you have no inherent protection of the material through its chemistry, what you can see under certain conditions is that the zinc will selectively leach from the brass and leave behind a spongy copper layer. NSF, as we said, NSF 14 allows no more than a 200 micron or 0.008 of an inch depth of corrosion in this standardized test, ISO 6509, before a part is considered to have failed. Brasses can be protected from this kind of dezincification corrosion either by reducing the zinc content to below 15%, but that makes it a lot harder to produce, or by adding an element that protects the brass, like the phosphorus content in alloy 693, or arsenic, for example, in alloy 35330. Those types of elemental protections or alloying addition protections work only as long as the zinc content in the alloy is below 36% and the proper alloy and manufacturing controls are in place. Under a microscope, stress corrosion cracking looks like this. It kind of looks like a lightning strike through the brass. As we mentioned, that's caused by a combination of high levels of stress, either from the production of the input material, the production of the part, or the installation of the part, and then exposure to something that attacks the grain boundaries of the brass. Typically, it's ammonia. Mercury will also attack it, but that's not typically found in your standard home environment. NSF 14 requires that materials that are used for PEX fittings have the kind of alloy composition that resists both forms, either stress corrosion cracking or dezincification resistance, just as a summary. Stress corrosion cracking performance can also be improved if you stress relieve either the input material, the input rod or forging, or if you stress relieve the machined parts to take the stresses out of the whole manufacturing operation, or by using, as we can show, alloys that contain silicon, which is a known stress corrosion cracking improvement addition. We talked about fire sprinklers in the home, and effective January 1st, municipalities have to start writing this International Code Council requirement, RB 64, into their municipal codes that say that 1- and 2-family homes have to start to contain fire sprinklers. That means PEX fittings. So PEX fittings means that you have to meet those corrosion requirements that we just talked about, but because they're part of your drinking water system, then they also have to pass the national legislation for the maximum weighted average lead content and the 5 part per billion lead leachate requirement. So there's all of those requirements on it, plus since it's part of a fire protection system, there are also some UL requirements that are even more stringent requiring or regarding the corrosion resistance of the materials that are used. And then finally, there's the Consumer Product Safety Improvement Act, which began in 2008 and had a maximum limit of what in children's products, children aged 12 and under, and dropped the maximum lead content from 0.06% to 0.03% in February 2010. And then on February 16th of this year, there was a public hearing to discuss the technological feasibility of dropping the maximum lead content to 0.01% or 100 parts per million. So what alloys can respond to all of these changes? This is an example of a number of the copper alloys that are available that you might deal with or you may see or be asked about. In blue is the standard alloy 360 that's been the predominant alloy of any rod alloy for a lot of years. The first ASTM standard for alloy 360 dates back to 1917. And alloy 360 always contains 60 to 63% copper, 2.5 to 3.7% lead. But in October of 2010, the ASTM standard was changed to drop the maximum lead content from 3.7 to 3.0 so that alloy 360 could be used by some component manufacturers in their drinking water contact parts. Beyond that, there are some other what are considered to be high-leaded alloys that are in the white rows. And then there's a series of low-lead alloys that are in the yellow rows. And low-lead is defined really by users depending on their part design or their component design. And then there is, in the green row, alloy 693, which is considered to be a no-lead alloy. But that definition comes from the Environmental Protection Agency, which sets a 0.1 maximum lead content. So anything below 0.1 lead is considered to be lead-free. There are some dezinkification-resistant alloys in this table, 35330, which contains arsenic and has a relatively low zinc content by virtue of the higher copper level. There's a European alloy, CW511L, which contains arsenic. There's a 693 alloy, which contains phosphorus. Alloy 363, which contains phosphorus. And potentially those alloys can be used in some of these NSF-14 controlled applications. When you look at the impact of lead on the different kinds of brasses that are there, alloy 360, which in this case has 2.7% lead, is a combination of brass, a uniform copper and zinc mixture called alpha phase, and then lead particles. Alloy 27450, which in this case has a maximum or has a 0.17% lead, there's really hardly any lead there to see. These tiny little specks are lead particles. Mainly, this alloy is a mixture of the uniform copper and zinc alpha phase, and then when you get above about 36% zinc, then you start to have zinc separate out in a high zinc phase called beta, and these are particles here, are beta phase. And then you get to some of the lead-free alloys, in this particular case 693 with 0.05% lead, there's no lead to see. And where in alloy 360 the lead particles break up the chips during machining, in alloy 693 and other lead-free alloys, there's something else in there to break up the chips. In this particular case, you have the lighter colored kappa and gamma phase that help break up the chips. There's other alloys that might contain bismuth or tellurium, and those would be present as discrete particles in the matrix and break up the chips for those particular alloys. If you're relying on lead for machinability, then there's a relationship as shown by the curve here. As the lead content goes up, the machinability vertical axis, you can see goes up. Or conversely, as the lead content comes down, the machinability comes down. And legislation that we've been talking about has been driving the lead content to lower and lower levels, so that in order to get maximum machinability for people who are machining these water components, other avenues have to be pursued. For example, what does not fit on the curve is alloy 693, which uses that three-phase microstructure to get much higher machinability than you would expect based on the lead content. As I mentioned, there are some other alloys that contain other materials, whether it's bismuth or tellurium or sulfur, that do the same sort of thing. They have very low lead contents, and they have higher machinability levels. But the thing that isn't obvious from this is that once you get away from using alloy 360, which was the high-leaded predominant alloy, there are a number of differences that have to be recognized and adapted to regarding machining practices and even corrosion behavior that mean that it's not just an automatic switch for a user of alloy 360 to some of these other either low-leaded alloys or lead-free alloys. The alloy selection has to consider if there's any corrosion-resistant requirements for the application and whether the new material can meet those corrosion requirements. So, for example, for NSF 14 applications, you have 3 alloys that meet the maximum 200 micron dezincification depth pretty handily, and then you have other alloys that can occasionally show dezincification levels above that 200 maximum, and then you have other alloys that just plain don't meet it at all, including the industry standard alloy 360, which works fine and has worked fine for decades, but now is disqualified from consideration for NSF 14 applications. There has been a proposal to put that same sort of dezincification resistance standard into NSF 61 for drinking water components, where the main concern in the past had been 15 parts per billion lead leachate. Now it's going to be 5 parts per billion in 2012, and there's a committee looking to see whether it's appropriate to put that into that same dezincification resistance requirement for NSF 14 into 61. So technically speaking, there you have it. Legislation's disqualifying proven alloys because of its lead content. Corrosion concerns are likewise eliminating traditional alloys because they cannot meet the NSF 14 requirement. But new alloys are being developed to meet these legislative requirements. But you have to consider that they've got different properties, different production needs, plus they need to be tested to ensure that they meet any other requirements outside of just the lead consideration. We use information like this to provide technical assistance to help customers to be compliant with these new requirements, but there's only so much that we can provide. At some point, then, users of these different alloys have to do their own in-house testing or the testing that's required by third-party certifiers to make sure that they meet all the needs. So for me, I'd like to thank you for your time and attention to such a technical subject, and here's Tom Christie to conclude this portion of the webinar.
Well, just to mimic Larry's comments, we certainly appreciate the opportunity to share this with you. As you can see, part of the challenge we're facing as a brass rod producer is the standard vanilla that we love to produce is under constant pressure, whether due to lead legislation or corrosion resistance legislation or a variety of others. And so we're quickly having to go from vanilla only to Baskin-Robbins as far as making a multitude of products. We're working hard to identify new options and alloys that will meet these requirements, but we're really a production facility, not an R&D facility, so it's hard to make a small batch of anything for a trial. But we are working closely with customers to do that, and that is our plan to continue to do that. and we certainly have a strong technical support team available to answer questions that you may have regarding any of these alloys. So please don't hesitate to contact us for additional information. As you can see there, my email is listed above. If you do want some of the key legislative information in this presentation, we can provide that to you. And then I also ask you to stay tuned. We're working what we think is another major opportunity in the copper industry. We're working to develop a presentation related to antimicrobial benefits of copper and copper alloys. We think that this does have some opportunity to help offset some of the pressure to convert away from copper alloys that we're seeing currently in our customer base to plastics and other materials. We think some of these benefits of antimicrobial could help identify new opportunities into the future. So again, we thank you for the opportunity, and please let us know if you have any questions.
All right. Thank you, Tom and Larry. We really appreciate that excellent information. Just a reminder that if you have questions for either Tom or Larry, please go ahead and send those to us. We do have a few here that we will get to. Also, just so that you know, about an hour after this web seminar closes, you will receive an email with a survey link that we'd like your feedback on. Also, a reminder was what Tom said, that if you would like additional information or on the information presented here, to contact Tom directly, and they'll help you out as best as possible. So let's see here. Let's go to okay. What controls will be in place to confirm that offshore brass meets these new legislation requirements and standards?
Well, speaking for what I know about California, their Department of Toxic Substances Control is required by state mandate to sample at least 75 different products a year for conformance to the California AB 1953. I don't see anything like that in the national legislation. I don't know if there's going to be more legislation to come, or they haven't considered that. But outside of California, there is currently no control.
Most of our customers are taking the position that the legal community will likely be the ones enforcing this. You know, as you know, in particular in California, it seems like the lawyers are eager to go after any company not following the rules. So our interpretation is, although that is in place for California, the legal community may be playing a role in that for those companies not complying with this legislation.
Okay, great. And do we have any other questions for Tom and Larry? We'll just give it a couple more minutes here. And, you know, we really appreciate everyone attending this morning, and we really encourage you to let us know what other kind of subjects you would like CAVSA to conduct web seminars on for you and others within your organization. So by all means, please forward those to Wes Huddleston. That's W. Huddleston, Hudelson, at copper-brass.org. And you know, let us know. Also, hopefully most of you will be with us in Austin at the end of this month for the annual convention, and be sure and let us know. I will be there as well as a few other staff members, and any feedback you have is always very much welcomed. Let's see here. Now, Tom and I know that Jim Palmer from Chase is going to be at the convention. Will either of you gentlemen be with us?
Yes, this is Tom Christie. I'll be attending.
Great. So if anyone has additional questions. Okay, now we have another question here. What is the main new alloy being used now for water applications?
That's an excellent question. Quite honestly, we wish we really knew that answer clearly defined. All of our customers are working hard to identify their path to compliance. So the simple answer to that is it really depends on the specific product and the specific application. Something with a more complex waterway like a faucet, it could have a myriad of products. It could have 370, 360, 2745, and 693 in it. Because, again, they are able to use the total wetted surface area of that water pathway. If you've bought a new faucet recently, especially from some of the big box stores, you may notice that they have a much extended water connection line coming out of the bottom of the faucet. Part of that is, again, to extend the water pathway so that they can get away with using a more traditional alloy. For the more of the fittings and valves market, we're seeing more of a focus purely on the lower or compliant alloys, which would be like your 2745 or your 693, those of which with a maximum of 0.25, because they're typically dealing with a all-metal pathway that has to be compliant.
Okay. Any other questions for Tom and Larry this morning? Let's see if we have anyone else who has something. We'll have just a couple more minutes here. Give it a couple more minutes. Okay, let's see here. We have a question. Oh, here's a question. Do you know if the brass industry was represented in Congress as these laws were being discussed and so forth?
Yeah, I believe that the Copper and Brass Fab Council had a representative there. The California Metals Coalition had representation for the AB 1953 work. I believe that's it.
Okay. All right. Any other questions for Tom and Larry this morning? Okay. It looks like there are no more questions right now. So unless there's something in addition that the two of you would like to add at this point?
No, just again, we appreciate the opportunity and would be happy to handle any other questions or send out some of this content if there's interest.
Great. All right. Well, we thank all of you for attending this morning and look forward to having you with us on our next web seminar. And again, we look forward to having you with us in Austin. So have a wonderful day, and we will talk to you soon. Thank you, everyone.